Hi there, Physics 152. This is Jason Harlow, your practicals coordinator. This is about the very last week of practicals. You will be doing a free choice experiment at your pod, and you might sit at a different table or something. So you may not know this, but physics has been taught here at University of Toronto for 180 years. It's a long, long history, and we have a whole lot of teaching experiments in storage around. And some of them are super cool, and a lot of them are related to quantum mechanics in some way. But usually we only have one setup of each apparatus. It's these things can't really be bought at stores, and can be a little expensive to build. So I've selected 8 of the best ones that I think would be really fun for you guys to do. And you and your pod will be able to choose to do one of them. So, I just want to take a look through the list. We'll start off with pod 1. There'll be the acoustic interferometer. It doesn't look like much on the outside. It's basically a wooden box, and you can see various wires going into it. But if you peek to the inside, it's actually a Michelson interferometer, but for sound. So there, instead of there being a light source, there's a sound source, a speaker. Instead of a mirrored beam splitter, there's an actual piece of paper which will transmit some sound, but also reflect some sound. And then there's a wall on one side and another wall which can be moved. And then there's a microphone. And so you're measuring the wavelength of sound in much the same way as you use a Michelson interferometer to measure the wavelength of light. On pod 2 is the gyroscope. It looks like this, but basically it's a thing that spins, and in fact, atoms and subatomic particles also spin and have angular momentum, and when they're subjected to external forces, which in this case is gravity, you can get precession and nutation. So it's motorized, and you're hanging little weights off this thing and really learning about precession and nutation. So that's a fun one. On pod 3 is the torsion pendulum. Here's kind of a picture of it. Basically, you get the apparatus is in a little chamber with a closable door. It's not a vacuum, but we're trying to prevent air currents, and there's a torsion wire, which is looks like it's about 40 centimeters long. And at the bottom are various objects that you can hang. And when you hang them, they oscillate around, rotationally oscillate around a vertical axis, and you can measure their moments of inertia based on that simple harmonic motion. On pod 4 will be E over m for an electron. This is perhaps maybe the most modern looking experiment. There's a couple of dials in the front, and basically what you're doing is you are producing electrons, free electrons in a vacuum, with a little filament, and then there's a potential difference between 2 grids which accelerates these electrons. Then you place the whole thing in a magnetic field which is generated by those coils you see around, and the magnetic field curves the path of the electrons. And you can actually see them. They glow as they travel along because they're high energy, and then you can try to measure the radius of curvature, and depending on the ratio of the charge to the mass of the electron, you expect different curvatures for different currents. So you can measure that fundamental number. On pod 5 is spectra. This is sort of my favorite. I think I like this one because I'm an astronomer and I like to look at spectra of stars. But for this, you're looking at spectra of tubes of ionized gas. And so there's a spectrometer and an eyepiece. And when you look through the eyepiece, you will see various lines which are particular wavelengths where the gas is emitting, and then darkness in between. And it turns out that every different element will have its own pattern. If you scroll down here, you'll see some tables. Like helium has its own pattern or fingerprint, I guess, of lines that you would expect. And argon and krypton, they all have their own lines. And so you'll get a few tubes. Some of them you'll know, and some of them, one of the tubes, you won't know what it is, and you'll have to use a spectra and make a measurement to determine what's in the tube. Lens optics, another good optics one. That's sitting on pod 6. This is the thin lens equation, which is 1 over the focal length of a lens equals 1 over the object distance plus 1 over the image distance. So that's your basic setup. You will have a real lens and a real object and be getting well-focused images and exploring this equation. On pod 7 is the scattering experiment. This one is highly cool. So basically it has to do with particle accelerators and how, for example, at the Large Hadron Collider, you collide some high-speed particles with a target. And the target is so small that you can never observe it except by looking at what comes out of a collision. So the particles go in and then they collide in some way that you can't really see, but what you do see is what comes out. And so that's exactly what you're doing here is you're taking, in this one, it's what you're actually doing is taking tiny little BBs, and there's a blow gun, and you squeeze the gun and it shoots the BBs at a little target, and you can clearly see what the target is, but it might have different shapes. But what you're supposed to do is analyze where the BB comes out, and there's little ticker tape and where you can see a little collection of for different impact parameters, what angle do the little BBs ricochet off. You can infer backwards from the collision pattern or the angle pattern what the target shape is. So really good if you're ever thinking about doing high energy experimental particle physics. This is good practice. And lastly, the Wilberforce pendulum. This one seems very mechanical in nature, but in fact it's quite related to quantum mechanics. So what it is really is it's just a mass on a spring, but the idea is that the spring has both a translational period, it bounces up and down, the mass bounces up and down, and it has a rotational period. You can actually, it's like a torsion pendulum, it twists around. And with the Wilberforce pendulum, what you do is you match those two periods or match those two frequencies so that you get a resonance between two different oscillation modes. And this happens a lot in small things, in atoms and molecules. And when that happens, you can end up with the energy kind of sloshing back and forth between the two modes. And so you get an additional period where for a while, for a moment, it will be entirely just rotating. And then after a while, all of that energy will have gone into a different mode, the translational mode, and be bouncing up and down. So you may be wondering, how do you choose which free choice experiment you're going to do? Well, that will happen during practical 9. So during the week, while you're doing the wavelength of light experiment with the lasers and the double slit and the single slit, what's going to happen is that your pod will be given a random order, and I think it's going to go by cards. You'll get a card, aces high, and the one with the pod that has the highest card will send a representative or make a choice somehow of which experiment that's remaining that you want. And then if your TA will find practical 10 experiment number, which is an item, and for everyone in your pod you will enter the number 1 through 8 of the free choice experiment, so that we all have a record of which experiment you're planning to do. And at the same time, it might be a good idea to pick your practical 10 roll number as well, and so that you've completed your whole set for the semester. And speaking of rolls, last thing is that there will not be a specific theory video or experiment video for all of the 8 experiments, but still, you know how to do these rolls. Hopefully you can be a lead theorist, but kind of thinking about the theory more, or be the lead experimentalist in that 10th week. So that's it. I hope you have a great time with your free choice experiment, and then I hope you have a great summer. This is my last video, I guess. Okay, take care. Bye for now.